Alright, I will get this in frame. I don't know, eventually I'll rethink this so this is less... There's still something awkward about the situation. I mean, this works better than some things I've done, but...
Oh, it's better than the 3 people when we had me, Daniel,
yeah,
and
three
Nathan
people
in here.
in here just is, that's too much.
That was hard.
It was. Alright, I will begin with a word of prayer again. So, Heavenly Father, we, again, Lord, thank you for this time we have together. I just pray that you'd bless this work. And we thank you, Lord, for your many blessings. In your name we pray. Amen. Alright, so I want to just talk to you guys about, a little bit about, so the way this is going to go is, I showed you some elementary results, and so I'm going to be skipping around a bit. At the end of it all, we'll know everything, but maybe a little bit disorganized, and it'll probably be the case that we come back to stuff a few times over. But I'm just going to kind of forge ahead as best as I can and see where it takes us. So the next thing I would typically talk about, well, I guess there's two kind of different ways to go. Sometimes I would talk about Fourier series and stuff to start with, but I think it's more fun to sort of motivate why we need to study Fourier series. So the simple answer to that comes from studying heat equations. So what is a heat equation? Basically, it's a partial differential equation. So we let U equal to U of T comma X. So U is the temperature at time T and position X in whatever units you care about. It's some kind of one-dimensional thing. I mean, it could be a two-dimensional thing, but it's homogeneous in the sense that, like, it's got the same temperature at each X position, and or it could have different. Maybe it has different temperatures at each X position, but we don't know about them. I don't know, but this is the starting point. And I think Logan, that chapter 1 in Logan that you guys are reading, is going to give you much more insight into that sort of thing. So here's the heat equation: UXX equals to alpha UT. Or to be more explicit, partial squared U partial X squared is equal to alpha partial U partial T. So this is the one-dimensional heat equation, and alpha is a constant, right? A positive constant. And here's the deal. We want to study the time evolution of temperature of this object. And again, for reasons I don't want to explain today, that partial differential equation models the temperature as it changes. So basically the idea is you study this equation to understand how the heat dissipates along a little rod of length L. So we look at 0 less than or equal to X, less than or equal to L. So, and let's see here.
So in this rod, are we assuming it's like the disc of the rod is like all the same temperature?
Right. Yeah. So it's like it's kind of a boring homogeneous. It's like a pipe or something, right? So
we're just treating it as a single line.
Yeah. You could exactly. So the it's such that the temperature is the same at each cross section, and so here's like X equals to 0 over here. X equals to L. Like that. Alright, so alpha is a constant determined by the particular physical characteristics of the object, and we're going to suppose that we're given some sort of at t equals to 0, then you were going to assume that U of, let's see here, 0 comma X is equal to f of X. So this is the initial temperature distribution. Alright, and then there are various boundary values that you could place on this thing. For example, we could, we have all 4 different choices. So I think if you study it more carefully, we're assuming that it's that heat can't escape from here, it just kind of spreads out. So, but you could either fix the temperature at the ends to be 0, like think about holding each end of the rod in an ice bath like that. If you assume that the derivative in time, right, if you assume that partial u partial t is equal to 0, at 0, that would say that the temperature doesn't, I think I'm saying it wrong. Sorry. So yeah, u equals 0 and u of 0 equal to u of 0 comma, sorry. I'm just, it's the derivative I'm getting confused. Yeah, I'm sorry. It would be, I have the wrong derivative in mind. The perfectly insulated end would be partial u partial x equal to 0, and both x equal to 0 and x equal to L for all time. And then you can look at other cases like left end 0 temperature, right end insulated, or left end insulated, right end 0 temperature. So there's like 4 different choices corresponding to fixing at 0 temperature, or not fixing the temperature but insulating it. Insulating you could capture by like insulation here. You could capture by this partial u, partial x of 0. Sorry, t. T comma 0, yeah, equal to 0 for all t. That would be putting a perfect insulator there. So you could do that on either x equal to 0 or x equal to L, or you have these different things we could imagine. Either putting perfect insulators or fixing the temperature, like in an ice bath or something. All right, so I think we will, for the sake of specificity, in my notes I've got all 4 different cases unraveled, but just, for the sake of being concrete, let's look at case 1. Both I call it case 1 in the notes. It's page 205 of these notes. I'm not sure if you guys, I haven't told you guys to get them, so you probably don't. Oh, case 205, what's wrong with me? Case 1, page 205 of my notes. So 0, both ends at fixed 0 temperature. So in other words, we have u of t comma 0 equal to 0, and we have u of t comma L equal to 0, and this is for t greater than 0. Okay. I mean, we're assuming that the initial temperature distribution is given at time 0. We want to see what happens for t greater than 0, right? That makes sense? All right. So if you look at it, we have a couple different things going on now. We have these boundary conditions, right? But we also have an initial condition. So these are the boundary conditions. What's our initial condition? The initial condition in this case is u of 0 comma x equals to f of x, right? F of x is some given but arbitrary temperature distribution. Eventually we'll solve this problem for specific choices of f of x, not too long from now. Alright, so, and then of course that's the data that we have to satisfy, but we also of course are looking for a solution to the heat equation, because that describes how the temperature changes according to heat flow. Alright? So we're trying to solve this u xx equals to alpha ut. That's our goal. We want to solve, this is the problem, this is the heat equation with fixed temperature at both sides and a given initial condition. Alright, so this is where I will show you, this is the technique that's used, it's called separation of variables. Not, not the separation of variables you saw before, like the start of ODEs, right? That's a different separation of variables. But here it is. So what we do is we propose that u of t comma x is equal to big T of t times big X of x. So like, let it be understood, our notation is pretty nice here. Like t prime, what's that have to mean? That means dt dt. In contrast, x prime means from context dx dx. Big X for the dependent variable, little x for the independent variable, just convenient notation. In writing, there's no danger for confusion. In talking, perhaps there is. All right. Okay, so then what? You feed this proposed separation of variables, right? And differential equations. Whenever we face some problem, some new problem, we can be creative, right? We can propose some guess of what a solution might look like. And if you think long enough and hard enough about it, your physical intuition and experience with problems that you already know how they behave might actually suggest to you to do something like this. I don't think that's immediately obvious, but I think in retrospect it might be as we look at the solution sets eventually. I don't know, that's just something I'm thinking now. I'm sure I'll think lots of new things this semester with you guys, because I've never really had a chance to teach this in an extended format where we actually had time to really unravel it. So I hope you'll bear with me as we discover what I don't know and what I might learn. Anyway, so all right, so you plug back in this, like you said, plug it in, see if it works, but it won't be so bad. So we have to do what? Partial squared, partial x squared of tx, right, is equal to partial t of tx, right? So how's that go? Well, t is a function of time alone. So this guy, you get to pull out like so, right? And on the other hand, on the other side, x is a function of x alone. Partial t is a constant with respect to this partial differentiation, so you pull that out. So what's that leave you with? Just leaves you with t x double prime, all right, equal to t prime x. And I do believe I have neglected a kind of important thing, which was what? I'm not trying to set alpha to 1 here. I'm trying to be a good citizen here and keep alpha keep alpha arbitrary, and it's there. All right. So then what, guys? Based on labeling, I called it separation of variables. So you're not
separate the variables.
Yeah, separate the variables. I mean, that's not the logic there isn't terribly deep. Okay. Anyway, it's just a natural thing to try. So basically, divide both sides by the solution again. So dividing by the product of x and t leaves me with x prime prime over x equals to alpha times t prime over t. I'm gonna leave the alpha on the t side. Make sense?
Just out of it.
Yeah. Now here's this. I don't know why this is hard for people to. I guess it's just a new observation that makes it so controversial to many students. But you got to think about this. On this side, we have a function of x alone. On the right-hand side, we have a function of t alone. how is it possible that a function of x can be equal to a function of t? For genuinely independent variables, what's the only kind of functions which they all share?
The original equation, right? Or, well,
I mean, I suppose I could differentiate this another time. Like if I take the derivative of this equation with respect to x, that gives me partial x of x prime over x. I mean, here, I mean, I never do this, but it just occurs to me this might be convincing to some people. I don't know. Take the partial derivative of this with respect to x, what do you get? Right, because the x derivative of a function of t is 0.
Right.
But what else do you get? Of course, that derivative is also 0, right? Because on the other side, the x derivative, the t derivative of x prime over x is 0. How can this be? The first equation says what? It says, this says that x prime over x is equal to some function of, I need some other, let's say f2 of t alone, right? Would you agree? It has no x dependence, so the only thing that it can, doing a partial integration, so to speak, with respect to time, both sides there, how to say this, I mean, excuse me, partial integrating with respect to x both sides, I get that it's just a function of time, right? On the flip side, this says that alpha t prime over t is just a function of x. Oh, curses, I'm still back to square one again, dang it. Thought I had something here for a second there. I was trying to derive something. Fooey. That's not what I wanted to say. I mean, it's not wrong, it's just back full circle to where I started. Not helpful. Dang it. Don't know. Okay, so again, what is just, common sense inside my derivation was not as productive as I'd hoped. There's probably a simple derivation to do here to prove the assertion I'm about to make. The only way you can have this be a function of x and that be a function of t is if these are both equal to what? 0 is a possibility.
it's just a single case.
They equal each other, or they're genuinely independent, so they can't.
Maybe it helps if I give these names. Like this is Pac-Man and this is Ghost. So we need partial Pac-Man, partial t equals to 0, and partial Pac-Man, partial x equal to 0. Maybe I should focus on the just call it Pac-Man, Forget the Ghost. What is this? I mean, if it's not changing with respect to x, and it's not changing with respect to t, and it's at most a function of x and t, what is it?
Constant?
Yes, it's a constant.
Seems like trickery, but it's true.
Yeah, that's it. That's all I'm trying to get you guys to say.
Oh, I see, yeah, because it's still technically a function of, yeah.
Right? So that's the place where functions overlap. And we call that constant k
I see.
in order to make the link.
That makes sense.
So, oh my goodness, all of a sudden, what do we have? We've got to solve x prime prime. Tell you what, I'm going to make that a minus k. So then we have to solve x prime plus k, x equal to 0, right? And also, how's it go? I'm in between step here. Alpha t prime over t equal to minus k. In other words, t prime is equal to minus k over alpha t. Now this, of course, I can rewrite as dt, right? Oops, sorry, I'm off the edge of the world. And okay, so well, this I can solve by just garden variety first semester separation variables, or about 3 different techniques we learned. I mean, Laplace transform, or I don't know, whatever you want. I mean, there's so many different ways to solve this. But however you do, the solution is just what t of t is what it's e to the minus k little t over alpha. Okay. Times the constant. But I'm gonna, since we're multiplying solutions to form our solution, I'm just gonna leave it without a constant, since we can. I mean, I can put a t naught here or something. I'll put a t naught. It doesn't matter. Let me just leave it 1. I mean, we need a constant in the overall solution, but we don't need one here necessarily. If you want to, you can put a c there. We'll just relabel it later or whatever. Okay, so that's it for the time piece. Pretty simple, right? For this guy though. Okay, so then we have to go back. Now we have not yet used the boundary condition or the initial condition, right? So now let's use the boundary condition. The boundary condition. Let's identify it for what it is. You have u of t0 equal to 0, and we have u of tl equal to 0. Those are not conditions on x just yet. But give us 3 seconds, they'll become that, right? Because this says what? This says that t of t times x of 0 is equal to 0. This says t of t times x of l is equal to 0. But the time solution is an exponential, so it's non-trivial. So I can extract from these mixed boundary conditions the pure boundary condition of the form we were studying in our last talk. Just like this, right? This says x of 0 equal to 0, and this says that x of l is equal to 0. Does that make sense? Now what? So we're back to proposition 8.31. We have x prime prime plus kx equal to 0, paired with our 0 at the endpoint boundary conditions. I guess I've got a big X instead of a little y. It's the same thing, right? So what's that tell us? That tells us that we have solutions xn, right, xn of x equal to what? Some constant. I have to look back. I personally don't. After I work with these for a while, it gets memorized pretty fast, but despite the fact I derived them for you guys like 3 seconds ago, I still don't remember.
Sine.
Yeah, you're right. So it's sine.
And then the simple one.
Bn sine of n pi x over L.
X, yep.
And k is n squared pi squared. See, that's important because while the x solution and the t solution are not directly linked, they are linked together by the partial differential equation. In particular, the ratio of x prime prime to x and t prime to t times alpha, both equal to minus k. So whatever is forced upon us by the boundary conditions for x, it bleeds in to the t solution through the choice of k. See, this k, same k up here, so that has to now, in retrospect, go back up in here. And so altogether, we find the a potential solution here. Un of tx, I use the n because it's the nth one. We've got lots of them. And something like bn, and you could set bn to 1 if you want, I guess. You know what, I'll leave it. I'm feeling, I have trouble making choices, you guys know. All right, n squared pi squared t divided by alpha. That's my t, and then what, sine of n pi x over L. What data does this solve? I mean, what does this do for us? This gives us a solution for the partial differential equation, right? That satisfies the boundary conditions, right? And what else?
Wait, is the, for k, the L squared, is that just merged into another one of the constants on the exponent?
I probably missed my L squared. Let me think about that.
Should it be there?
N squared pi squared over L squared. N squared pi squared over, yes, there's an L squared right here. Thank you. Cool. Yeah. It's nice to have L equal to 1.
Yeah. Yeah.
Right, L equal to 1 is the problem I like to work in class if I'm doing something numerical, because it makes things a lot, prettier. Now, what have we not? So this does what? This, up till now, not necessarily in sync, let's say, with the initial condition. What about the initial condition? We haven't satisfied that yet, right? And we've got infinitely many of these eigensolutions, so to speak. So let's see here. Let me show you one where we can. Let me just make up an initial condition where we can straight up solve it. So suppose you knew that u of 0x was equal to, I don't know, suppose it was like sine of pi x over L plus 3 times the sine of 13 pi x over L. So I think about this is a linear differential equation, by the way. So the sum of solutions is again a solution. And that's why we need homogeneous boundary conditions, by the way. I would have trouble with the linearity structure if we weren't. These boundary conditions being 0 means that if I have 2 solutions which satisfy the boundary conditions, the sum of them still satisfies the boundary conditions. Right? A linear combination of solutions still satisfies the boundary conditions. If I was looking at like both of the n's fixed at temperature 3 or something, if I add those solutions, I'd have temperature 6. You see, that's going to be a whole different ball game, and that's why there's a separate chapter on non-homogeneous boundary conditions, which I've looked at, but it's been a number of years. I mean, this math does come up in my daily life, but me needing to solve it does not happen. So, basically, I can go, oh, okay, I know what these are coming from. I look up here and go, well, common sense tells me my general solution, I need to pick up n equals to 1, right? And n equals to, what, 13? And apparently I need coefficients of 1 and 3. So I can read straight up my solution. This will work, e to the minus pi squared t over alpha L squared sine of pi x over L plus 3 e to the minus 169 pi squared t over alpha L squared, sine of 13 pi x over L. And there you go, that's a solution. That's a solution to the boundary conditions and that initial condition. And that will describe how the temperature on this rod evolves as you let time flow away from that initial condition.
That's nice.
Yeah, what happens as time goes to infinity, what you think should happen happens. Think about it, you're holding a rod, both ends, at temperature 0, right? The heat can flow in the rod, so the heat can flow out, out the ends. So what should happen after a long, long time? The whole thing should be temperature 0, right? So look at this. I mean, yeah, both of these suckers, they go to 0 eventually, and that's what you got. All right. But of course, this is a rather artificial initial condition I've shown you, right? I mean, what if the initial condition was something, a little bit, and I got to be careful, like the initial condition I think has to be, this is where I get into trouble. I think, I'm trying to think, initial condition, I might need to be careful to be consistent with the boundary conditions, right? Well, that's a question, I don't remember. That's one of the things we have to look for. Is it possible? Here's a question we can leave on the table to try to answer. Try to come back to it. Think about it. If you think of it and think of the answer, tell me another day. Are we allowed any initial condition here? I mean, certainly the boundary condition that we have forces a particular choice of K. Are we allowed any initial condition though? I feel like if the temperature is 0 a little bit after time 0, it shouldn't be able to jump instantaneously from some temperature to 0 temperature right after time. I feel like there should be a continuity in the temperature function. So if I'm right about that, and I'm not sure, but if I am right about that, that means that my initial condition also has to satisfy 0, right? So if I wanted to, it seems like I might get into trouble if I try to make my initial condition, for example, like u of 0x equal to x. That probably wouldn't be cool because at 0, I have 0, but at L I have L. So instead, I might want something like F's value of x minus L. Oh, that's still not good. That's still not much better. I'm sorry. What I was aiming for...
That was like the complete opposite.
What I was,
the rod.
What I was aiming for was something like these. So like 0 and L, here's x. And I'm just drawing u this way. So something like that, and this is a snapshot t equals to 0 of the temperature profile. So if that was my initial condition, that would satisfy the boundary conditions at time 0. And, right. So that would be something like u...
It's 5:00 p.m.
u of tx. Actually, I'm almost to a very good stopping point. This is great. U of tx is equal to, well, you could make something like x, say for 0 less than or equal to x less than or equal to L over 2, and then something like L over 2. What is it? No, it's L, rather. L minus, I guess it's just L minus x for L over 2 less than or equal to x less than or equal to L. For what it's for thing. Does that make sense? Is that continuous? put in x equals L over 2, I get L over 2 from the top case, the bottom case. Yeah, so L over 2. 0 at 0, at L, L minus L, 0. Okay, that's the formula. Right. You might remember how to re-express that in terms of a sum of products of gate functions from 334.
Yeah.
Yeah, okay. All right, so now this thing I just did down here, just like, I'm just eyeballing it. I need one of these guys and 3 of those guys. How about that? You know, how do you get that guy right there? How do you get this one? Like we did for my contrived example. I mean, which sign is that? You see we can't do what we just did, right? We need something more sophisticated. All right. So here's the technique. So what we do is I guess I can get rid of this. So what you do is you propose that u of tx is equal to a sum n equals 1 to infinity of b sub n e to the minus n squared pi squared t over alpha L squared sine of n pi x over L. Now, of course, you might worry about the convergence of such a series. What are the rules for calculating with such a series? Is such a series reasonable? Okay, those are all valid concerns. Studying those concerns led to many of the developments that shaped analysis as we know it today. Right? But we're going to not worry too much about those concerns. This isn't a course in analysis. This is a course in how to solve applied problems. So that's our general template. It's an infinite linear combination of the kinds of solutions we found. And we know from the linearity of the PDE, it still solves the boundary conditions, because every single ingredient solves the boundary conditions. And we can worry about the convergence of such series. Now the goal is to find B sub n's that fit the initial condition. So what does it look like to fit the initial condition here, right? So the initial condition is that u of 0 comma x equals to f of x, right? That's our initial condition. So on the one hand, we can plug t equals to 0 into this guy, right? And what's that give us? On the left-hand side, it gives us the sum n equals 1 to infinity, b sub n, sine of n pi x over L. Because the exponential of 0 is 1. Right? And on the flip side, we have this f of x. Right?
Okay. Yeah.
So the question is, how do you figure that out? Well, it turns out, and there's different ways to calculate this. We'll spend some time calculating this, but basically the story is this. You can write this as a sum of, let's say, I'll use a different letter, a sub n sine of n pi x over L, n equals 1 to infinity. Where these a sub n's are the so-called Fourier coefficients. There's in fact a systematic procedure we can do to decompose f of x into its so-called Fourier components and to write it as a sum of signs. pictorially, it's something like this. I mean, I can't quite do it justice, but you just keep adding them and adding them and adding them, and you know.
We actually, like, we did a MATLAB project. Our final project was actually using this, except it was a two-dimensional plane, like a disc instead of like just the rod. And then, yeah, it was really cool. Like, we went through the code and like our own code and did like the iterations. It just like almost like perfectly leveled off. Like in the beginning, like the first couple iterations, it just looked ugly, and then like the more you did it, like it looked exactly like it was supposed to.
So was it a two-dimensional problem?
Yeah, it was like a plane. Well, it was supposedly like an open disc instead of like just like a single point on like a line, like we're treating this rod.
So you're thinking
It was like
about temperature and a disk?
Temperature in a plate, yeah.
Okay, so that one.
Disc plate.
Yeah, that you're looking at this differential equation, uxx plus uyy equal to alpha ut. That would be the difference.
Okay, that's kind of neat.
And
the formula up there looked the same, except it was like a double summation. Then it had a cosine of the other part or something like that.
yeah, this. So you propose a product solution, x of x, y of y, t of t.
Mm-hmm.
When you separate variables, you end up with x prime prime over x plus y prime prime over y, because when you divide by x by t, the y and the t cancel, the x and the t cancel, and over here the x and the y cancel. But this is a function of x and y, this is a function of t, it's equal to a constant. And then you have to fit the boundary condition, which is more interesting because it's two-dimensional. We'll look at problems on a rectangle. There's where we'll find the cinches and coshas I was bemoaning, not finding yet. But that's later.
Yeah, it was still really cool to see, like just like you were talking about that.
Yeah, and so the question, of course, is how do you calculate the Fourier coefficients? I mean, in some sense, I could derive that for you here. Oh man, I think I was out of frame. Oh well. No, oh well. I just wrote this in case. I'm sorry. It's my. All I wrote was what this equal to alpha ut and then divide, so we get. I don't know why I'm writing this. I'm gonna write it again some other day. Okay, so anyway, getting back to, basically we want this equal to f of x, right? So what you can do, there's something pretty awesome, which is that the integral, right, of sine of n pi x over L times the sine of, let's say, I guess I can use little k here without any trouble, k pi x over L dx from 0 to L. Turns out that that's 0. So this thing is equal to 0 if n is not equal to k. The reason for that is simply this: the product of two sines gives you a cosine of a sum or a difference of the arguments, but because you're integrating the cosine of a sum or a difference over an integer multiple of wavelengths, those integrate to 0. It's a pretty straightforward calculation. And then when they're equal, you got yourself integral sine squared over what? Over half a period. The integral of sine squared plus cosine squared over a half a period is pi. So it's pi over 2. I could be wrong. We'll find out later. I'm just short on time, so I don't want to get into details. But anyway, normalizations aside, so basically what we're finding then is if we just integrate, you go up here and you integrate this series, assuming it converges, big assumption, all right, but make that assumption. And so if you just integrate, not disintegrate, but integrate, it looks to us like the b sub n is going to be, one more step. So if like integral of f of x times the sine of k pi x over L dx from 0 to L, right, is equal to, and so I'm integrating the series. Let's assume that integration and summation of the series can be interchanged. So we got like the sum. I'm bringing the integration inside the series, if that's okay with you guys. Bn is a constant. I'm trying to get our pause on it. And then we got the integral of sine n pi x over L sine of k pi x over L dx from 0 to L. By the way, this thing I could rewrite as pi over 2 Kronecker delta n comma k. So basically it's saying that that series, all those terms are 0, except for one case. N equals to k. So what we find then is that this, if you'll allow me this manga style calculation, right, the whole series truncates everything 0 except for k equals to L, which gives us pi b sub k over 2. So anyway, in other words, b sub k is 2 over pi, the integral from 0 to L of f of x times the sine of k pi x over L dx. That's the Fourier coefficient that we need here. So it's awful, but it's not impossible to solve the problem I posed here. All you have to do, right, is calculate these Fourier coefficients by doing the integral that results from plugging that piecewise defined function into this integral. But integrals of x times sine or L minus x times sine are integrals that you can do. They're not pleasant, but you can do them, and they'll give you functions of k, which then gives you the rather interesting and somewhat complicated formulas for b sub k. You take those, and that actually is, so this would be a sub k as well. I mean, the bottom line is here is you end up with these have to match, because these are like vectors. It's like a basis expansion. So these are the coefficients of the basis, they have to match up. And so that's actually a sub k in another way of thinking. So that's why Fourier analysis matters, because it gives us a way of building the solution that we want to match the initial condition from just building up, you know, individual frequency responses to each of the Fourier component of the initial condition. And this is more or less how you solve all of them, at least at the elementary level. It's going to be the same song and dance for the wave equation and Laplace's equation, just a little more wrinkles around the edges, but yeah. The thing that's kind of maddening from an analysis perspective, this little thing we did with flipping the integration and the summation, that's not generally okay. So actually, if you want to be careful with this stuff, you need to study the convergence of these series a little bit, and you know, we might end up spending a day or two on that in here. We'll see. But anyway, I best get home before I get the call. Thanks, guys.